I am Professor Isha Medirata. Today I am going to start with what basically a semiconductor is, properties of semiconductors and types of semiconductors. So starting with properties of semiconductors first. Let's see what a semiconductor is. So semiconductors are solid materials which have electrical resistivity which is between conductors and insulators. Common examples of semiconductors that come to our mind are silicon and germanium, SiGe. What exactly a semiconductor is? Looking at the valency of semiconductors, of these materials, you can say the outermost shell of semiconductors, that is the outermost orbit, it has 4 electrons. So just consider one atom and the second atom. What exactly happens in semiconductors? The outermost orbit of this atom, that is these 4 electrons, they share with the electrons of the second atom. We know that maximum electrons in any orbit can be 8. So 4 electrons of one atom and 4 electrons of the other atom, they share among each other, and this is what is known as formation of covalent bond. So basically semiconductors are materials which are formed of covalent bonds, that is sharing of electrons. Moving ahead, let's see what are the properties of semiconductors. Starting with the first property, we say that they are metallic in nature. Why do we say they are metallic in nature? They have a certain conductivity. Obviously the conductivity of semiconductors is less than conductors of metals, but unlike insulators, they have a higher conductivity, and that is the reason we say they are metallic in nature. Let's see what is the next one. They are said to be bipolar. What do you mean by the word bipolar? They are said to be bipolar because in semiconductors, carriers, that is the carriers of electricity, the carriers of current, they can be electrons and they can be holes. So we say they are bipolar. Moving on to the next property, we have semiconductors behave as insulators at 0 Kelvin. Why? Because in semiconductors, if you talk about 0 Kelvin temperature, the valence band is completely filled up with electrons. That means the outermost shell, the sharing of electrons among the atoms is done. There are covalent bonds present. But 0 Kelvin means no external energy. There is no energy for the breakage of covalent bonds. And so what happens? No electron will move to the conduction band. No atom is set free. And because there are no free electrons, there is no conductivity. And so if you talk about particularly 0 Kelvin temperature, we say that semiconductors behave as insulators. Let's see which is the next property. They have a completely filled valence band and a completely empty conduction band at 0 Kelvin. As I just explained, valence band is full of electrons because of the covalent bonds, but the conduction band is empty because there is no energy, there is no bond breaking, and so there is no electron in the conduction band. Moving on to the last property of semiconductors, it is said that semiconductors have a negative temperature coefficient of resistance. What do you mean by this word? What do you mean by negative temperature coefficient of resistance? Generally what we observe that if temperature increases, resistance is going to increase. But semiconductors are exceptional materials. Why? Because if you provide energy, now increasing temperature means giving energy. If you are applying energy to a semiconductor, the electrons which are present in the valence band will move to conduction band. That means I can say with the increase in temperature, there is a breakage of covalent bonds and the electrons are moving to the conduction. They are set free. And hence we say conduction increases if temperature increases. And that is the reason they have a negative temperature coefficient of resistance. Let's see what are the types of semiconductors. They are classified on the basis of constituents, on the basis of energy gap, and on the basis of impurities. On the basis of constituents, we have again two categories. The first one is elemental semiconductors. Let's see what elemental semiconductors are. Elemental semiconductors, they are composed of single species of atoms. What do you mean by single species of atoms? They have only one material or one type of atoms present. Some examples of elemental semiconductors are silicon, you have germanium, you have carbon, lead. So if I say silicon, it will have all silicon atoms only, and that is what is the meaning of single species of atoms. Let's see what is the second category of semiconductors on the basis of constituents. They are known as compound semiconductors. When you have the word compound, let's see what are compound semiconductors. Compound semiconductors are composed of two or more than two species of atoms. So it's clearly understood from this definition that they have more than two types of or more than two varieties of atoms. That means you can just say they are like combination of atoms. Now these compound semiconductors are further divided into two categories. One of them is known as a 3,5 compound. What do you mean by a 3,5 compound? They are compounds which are formed by the series 3 and series 5 of periodic table. That means elements which come under the third group and elements which come under the fifth group. Some examples are gallium arsenide, gallium phosphide. And the second category of compound semiconductors is 2,6 compound. Just 2,6 compounds are formed by group 2 elements and group 6 elements. Some examples of them are zinc sulfide, cadmium tellurium. Now, let us move on to the next category of semiconductors, which is based on energy gap. The first one is direct bandgap semiconductors. Let's see what direct bandgap semiconductors are. The acronym is DBG. These are the semiconductors in which excited electron falls and recombines with a hole to release a photon. Now, where is this excited electron present? It is present in the conduction. Now, when the electrons gain energy, they become unstable and they definitely will lose energy and come to a comparatively lower and stable level. So when they come back to the valence band, there is always already a hole present. They recombine with that hole and the energy is released in the form of photon. So for a direct bandgap semiconductor, I can say electron plus hole will give us a photon, that is light. Because the output is in the form of a photon, we say that direct bandgap semiconductors have radiative recombination. Radiative means output is in the form of light. Some examples of direct bandgap semiconductors, they are all the elements which are present in the 3,5 compound series. That is gallium arsenide phosphide, gallium phosphide, aluminium gallium phosphide. These are some examples of direct bandgap semiconductors. Now let us move on to the next category on the basis of energy gap, and that is known as IBG. Let's see what IBG is. They are known as indirect bandgap semiconductors. Semiconductors in which excited electron falls and recombine with the hole to dissipate heat. These are the materials which have different K values for minimum of conduction and maximum of valence. So in order to conserve momentum, what do? They just transfer their momentum to the lattice. And in this way, there are vibrations set in the lattice and that leads to heat. So because it's a two-step process, we say that indirect bandgap semiconductors always dissipate heat. Or else we can say electron plus a hole will give us heat. Because that recombination of electron with a hole is through lattice. And so the output is in the form of heat. Because the output is in the form of heat, we say that such semiconductors have non-radiative recombination. That means they do not emit light. Some examples of indirect bandgap semiconductors are silicon and germanium. Moving on to the next category of semiconductors on the basis of impurities, we have intrinsic semiconductors. Let's see what intrinsic semiconductors are. They are pure semiconductors which have no impurities present like silicon and germanium. So in short, I can say purest form of semiconductor is intrinsic. Let's see what the second category of semiconductors is on the basis of impurities. They are called extrinsic semiconductors. Let's have a look at what extrinsic semiconductors are. Impure form of semiconductors obtained by addition of impurities. Why is the need of impurity addition in semiconductors? It is to increase the conductivity. Now semiconductors, if you talk about semiconductors conductivity, it can be either increased by temperature or by addition of impurities. So we make the semiconductors impure in order to achieve a higher conductivity. Now these extrinsic semiconductors are classified into p-type. That is, what exactly is a p-type semiconductor? It is formed if a trivalent impurity is added. What do you mean by a trivalent impurity? It is a type of an impurity which has 3 electrons in the outermost orbit. Silicon already has 4 and this atom which is added will have 3. So now we have total 7 in the outermost orbit, but there is 1 hole. So p-type are the materials which have holes as majority carriers. Let me give you some examples of trivalent impurities. Very common impurities which are trivalent are boron, aluminium, gallium. Let's see the second type of semiconductors. They are known as N-type semiconductors, which are formed when a pentavalent impurity is added. Penta means 5. So they are materials which have 5 electrons in the outermost orbit. Silicon has 4 and you add 5. So now there are 9. That means 1 electron is extra, which is called a free electron. And hence we say these N-type materials have electrons as majority carriers. Some examples of pentavalent impurities are phosphorus, arsenic, antimony. Let's see extrinsic semiconductors in detail. So starting with the first type of semiconductor, that is extrinsic, is p-type semiconductors. As I just mentioned, p-type semiconductors are formed by addition of trivalent impurities. P-type semiconductors are the materials which have holes as majority carriers. Let's see what a p-type semiconductor is. Just look at the diagram. Here the diagram shows all covalent bonds in germanium. In the center you can just see a boron atom is added. As I said, boron is a trivalent impurity. What does that mean? Boron has only 3 electrons present. 4 of germanium, 3 of boron gives us 7. So you can clearly see 1 covalent bond in the diagram is incomplete. And that exactly is the concept of majority carriers as holes. Understand the energy level diagram or the energy band diagram of p-type semiconductors. Here I have just shown the valence band and the conduction band. In between them the energy gap, that is forbidden gap, is shown. Addition of boron. Now what does boron do? Boron is an atom which is deficient of 1 electron. So this incomplete bond will be complete when germanium gives its 1 electron to boron. So just look at the energy band diagram from the valence band. Now in this diagram, the valence band is of germanium, conduction band is of germanium, and in between them there is an acceptor level shown. This acceptor level is of boron. What does this mean? If you give energy, even at room temperature, electron from germanium will go to boron because boron already has 1 less electron. And that is the reason boron is also known as acceptor impurity. It accepts an electron from germanium, from the valence band of germanium, and that is the reason a hole is created in the valence band of germanium. And that is the reason we say holes are majority carriers. Moving on to the next type of semiconductors, that is N-type semiconductors. So let's have a look at this diagram first. Here in germanium you can see P, that is phosphorus, is added. Now we know that phosphorus is a pentavalent impurity. A pentavalent impurity means it has 5 electrons. So in the diagram you can clearly see that 4 covalent bonds are complete. but still left as a free electron. That means the covalent bonds are complete, but still we have a free electron. Where will this free electron be? Because valence is already filled. So this will be present in the conduction band. Now let's have a look at the energy band diagram. In the energy band diagram here, you can see the valence band. Now this valence band is of germanium, conduction band again of germanium. In between them, you can see a donor level. And this donor level is of the impurity that we have added. Now the impurity which we have added is already having one electron extra. And that electron it can easily give to conduction band. So what happens? This impurity, the free electrons of this impurity move to conduction band at room temperature or when energy is given, and so we have more electrons in the conduction band of germanium. And that is the reason we say N-type semiconductors have electrons as majority carriers. So this was just a brief about P-type and N-type semiconductors. This was just a brief understanding about the energy diagrams of P-type and N-type semiconductors. So today we have discussed what are semiconductors, some basic properties of semiconductors and the classification of semiconductors. Because till now we were under an impression if someone asks what are the types of semiconductors, we would definitely say P-type and N-type. But they are actually classified according to the categories we discussed today. Hope you have understood all the topics I discussed today very well. Till then, take care. Thank you.